Yeah, so it's been a while, but uh so I'll just quickly run through this uh Python notebook. So basically it's a quick credit first. So this is basically directly from this so-called SKLearn package. And this is exactly what they what they did to showcase the capability of their package, their library. So just let's say you wanna open let's say in Google Drive. So you can do a lot of things here. So let's say we have this new in Google Drive, there's a new button, and then more and Google Collab, you just be able to create a new collaboratory that's called a notebook. So you have a notebook and it's a blank one. And then if you let's say you open my link and then you want to have one at your local, not your local, but your own Google Drive, you can do so as save a copy in Drive. So I believe there is also a button somewhere there because for me it is I might need to go to let's check if it works, but maybe so I believe there is like a open in Google Drive or open a copy in a Google Drive, something like that, a button there, and then you can have your own copy. So you can just make any edits you want. So that is the trick. So basically, this is called nearest neighbor classification. And the data set we use here is called the iris data set. So this is a very classic, I would say classic data, the classic data set that you can think of. So let's say this, so what it's trying to do, let me show you a picture. So this is what we try to do here. We have this measurement of this iris flower here, and then we try to use the measurement to classify the flower into the three categories of iris out there. So I'm not an expert, but it's a setosa, versicolor, and virginica. Is something called virginica? Yeah, I think there are like three types, and then we use the measurement to categorize the flower into either setosa, versicolor, or virginica. So this is the task here, and then we have the measurement for the petal and the petal and the sepal. So just to give you a background. So what we do here is we just from this library called sklearn.datasets to import the load iris package. And then from the model selection, we have this so-called train test split. So what this is trying to do here is basically we just load directly from this, they call it some toy data sets available on the sklearn library that you can always play with. And there are different data sets. As I remember, there's something like a cancer cell detection, etc. So very interesting. You feel free to explore by yourself. And then what you can try to learn, let's say here is the sklearn datasets. You can just copy this sklearn datasets. You can go to Google and then you just, let's say you can just documentation. And this is how you learn about different toy datasets that you can play with. So diabetes, wine, etc. So here are some of the, so let's say we stick to this iris plants datasets for now, and then here are some quick introduction of the datasets. It's got 150 instances, so basically 150 rows. You can understand as 150 rows in this big table, and then 50 in each of the three classes. So basically, it gives you a like a data set of already matched. So with all the measurements, so let's say, let's have an example, but we can always come back to the data sets to understand better. So here we have this so-called iris. So this is the data set. So it has, so we see here it has got data. So it has, let's say the first row is a 5.1 length for the sepal, and then the width, and then the petals length and the width, and then has the label. So let's say for this observation 0, it has the target, so categorized as 0. So what does 0 mean? You might want to ask. So basically here it has got this feature names for each of the features. So we have 4 features, and for the target names, it has got these 3 target names. So 0, 1, 2, I believe. So, and one more comment about Python is it starts with 0. So for counting, usually we start with 1, but they just made this very unintuitive choice here. So it starts from 0. You see, it has got 150, but it ends at 149. So don't get confused. And then just a quick reminder. So if you want to run this box, you click this play button, or another way is Control Enter. Or if you use Mac, it's Command Enter. So here we loaded the data. So we assign X as the data. So here we started with 2 of the features because we want to visualize it later. So as human beings, it's always easier to visualize using 2 dimensions. So we stick with the first 2. And then for the target, we load the target as the Y. So keep that in mind. And here is another very key step, which is called train test split. It is because since we only get, we have like all the data as, matched data. So we have the outcome label for all the data points. So that's something we, if we want to make the best use of it, because we don't have anything for us to predict for now, but what we can try to use is, let's say we only use 100 out of the 150 for training purpose. So we train the model first. And then for the rest 50, we use that as a test. So we just put the model to test using that 50, and then we compare the predicted outcome with the true outcome. So this is the way of a very key idea in machine learning of how we can verify the effectiveness of the model, whether the model can do a good job or not. And we just put it to test using the so-called test sample. In the previous example, it's going to be the 50 observations. So here, I believe we have this train test split, but here it's gonna be, let's see. So I believe there's some default function here. So we have 112 rows times 2 columns here. So remember we have 150 in the original sample. So for the X train, we have only got 112 here. And for the Y, I believe it's even smaller. No, for the Y, it's gonna be the same, but this is the train. So for the test, it's gonna be smaller. So 150 minus 112 is gonna be 38. So here we have 38 for the test. It's gonna be, yeah. So we have, yes, for the training, as you said, so we have the output labeled already. So we disclose the labels to the model, so the model can learn from it. But for the test data set, we do not disclose the label, the outcome label. We only give the for example, here we only give the sepal length and sepal width to the model, and then let it make predictions by itself. And then we as the trainer here, we compare And then here, as we see, the test set is much shorter. We only got 38. So this is the X, and then you can also see the Y. It is also 38. Okay, if no, we will just quickly move on to building the classifier. So the way to build a classifier here is, again, we use the SKLearn packages, and this package is so-called the neighbors, and we import this K-neighbors classifier. And then so this is the one key package we use. And then here's another one called pipeline. So pipeline, basically, it simplifies the whole training process by just so you can just stick to like one line of code, so that can help you do all the training processes. So in the traditionally maybe a couple of years ago, when this package was not that mature, people gonna just have to run like write all the steps, basically what we just introduced in the slides, etc. So those are very time consuming, and just to use this pipeline to simplify this process. And then we also have this preprocessing package. Basically, it's just gonna be helpful if you have the features that are of different scales, or you want to make them look a little bit more balanced. But since here we only have the simple length and simple width, so which are all in centimeters and all in the similar I would say similar measurements. So we do not bother with any complicated scaling methods. And then this CLF stands for classifier, and then people like to use this abbreviation here, always use CLF. And then basically this code you don't need to remember. It's when you search online, it's all over the place, but you just get a quick idea. So you build the model here, and the model is going to be stored here at this so-called CLF. And then we specify the number of neighbors here as well. So we have this K equals to 11. So this is the K we referred to in the slides. So you look at the 11 closest neighbors, and then let them each cast the vote, and then you just use the, let's say here the category, you just use the category that has got the most the highest votes, and then we use that category as the final outcome. And here the code's getting even more complicated, but I will just give you a quick intuition here. So basically it shows how the decision boundaries can look like. So here the key here is we use the two different ways of calculating distance in as specified in the so-called model parameters. So we have the uniform versus distance. So if you want to know more, you just go to, let's say, this SKLearn documentation. So we have, I believe it's in the K-neighbors classifier documentation, but I think I'm overrunning. But basically, you just go to the documentation and search and learn. So here, I just want to give you a quick intuition of what it looks like. I think after you run all the like the code snippets till this step, you should be able to generate these two graphs that basically gives you very visual, very intuitive sense of how the K nearest neighbor algorithm is doing the job. So here the classes, the dot color, basically they are the real categories. It's not the predicted. So if you count, I believe here is gonna be the 38 test examples. So we have the 38 test examples here. Let's just to focus on the left-hand side for now. So we have them colored nicely, and then they basically, and you also ignore the background color as well. So we have the different dots. We plot them in this graph with the 2 dimensions. So the first dimension and second dimension as centimeters. We just plot them here. The K nearest neighbors algorithm help you achieve here is it helps you draw this zigzag lines here and then separate them into categories. And these zigzag lines are the so-called decision boundary, this decision boundary. So with these boundaries, whenever you plot a new dot here, let's say it's where my mouse is, let's say it's right there, and then it's gonna be the purple color, which is the setosa. So if it's here, it's a setosa. If it's here, it's a virginica. If it is here, it's still virginica. So this is basically intuitively how the classifier help you achieve this task. So you might want to notice is there are some wrong classifications here and there. So I think for the purple color, it does just well in this left-hand side graph. But just I think this one got misclassified as versicolor, but it should be setosa. And then for here, we got more like yellow dots misclassified into this versicolor region, and then vice versa for the virginica. It's the same. So you change the parameters. So these parameters, the model has got, I believe, at least maybe 10 or 20 different parameters for it to tune. So this is some people you may heard of the term called fine tuning. So this is the process of fine tuning the model. I would say the simplest way of putting this step. It can get really complicated, but this is a very simple like a demonstration of how your model can be tuned. So you can quickly observe that it does perform better. So let's say for this point, this dot, the setosa got correctly classified. It's not misclassified here because you can see here, let me just zoom it a little bit more. You can see here, it's actually purple color. It's the setosa region. Instead of the versicolor on the left-hand side, it got correctly classified. So when you look at the whole test sample and then you calculate how many it got correct and how many it got wrong, and then you calculate the percentage. So that is the most like a basic like accuracy calculation. And then you will find that when the weights equals to distance, you have a more accurate result. And then in that case, you're gonna stick with the parameter set as distance. So this is a way like why people always say like you train the model. It is basically you're tuning the model a little bit by a little bit and then a little bit more, and then it would until it perform the best within the test sample, and it cannot perform even better. And then that's the point you stop, and then you save the model for future usage. So this is basically the full process of how a model can be trained and how it is used in the real, like in action. So it's very simple and short demonstration.